In this short video, we're going to learn how to execute a cost minimization problem when we have a perfect complements production function. Let's consider a firm that manufactures carpets using labor and capital. To produce each carpet, the firm has to employ exactly 1 unit of labor and 2 units of capital. As a result, their production function is given by the minimum of labor and capital divided by 2, where L is units of labor and K is capital. The price of labor is $20 and the price of capital is $60 per unit. The firm's goal is to produce 200 carpets. We want to know, in order to minimize their costs, how many units of labor and capital should they hire? What do we need to know to answer this question? We just need a production function, an output goal, as well as prices for our 2 inputs. How do we approach solving this question? We know there is not going to be a tangency condition because the isoquants for this production function are those right angle shapes. So instead, we're going to use the no waste condition. The no waste condition is that the arguments inside this minimization function have to equal each other. So L equals K over 2. And in addition to that no waste condition, we have to meet our production goal. So we have our isoquant condition, which tells us that the output in this case has to equal 200. So we have a no waste condition and we have a production constraint. 200 units must be produced. So we're going to see how we solve this question. Here's what we know. We know the production function, the wage, the rent, and the output goal. We are trying to find the cost minimizing choice of labor and capital. The first thing that we're going to do is be explicit about identifying that no waste condition. So the no waste condition is that L is equal to K over 2, and we can call that condition 1. Then we also want to write down our isoquant condition, otherwise known as our production constraint. In this case, in order to write down the isoquant that our solution has to be on, we just take our production function, minimum of L and K over 2, and we set it equal to our output goal of 200. This is a sort of like drawing an isoquant and saying we have to be on this isoquant. The no waste condition says we have to be such that L is equal to K over 2. We'll call this second equation 2. So from here, what do? We're going to substitute 1 into 2, and we're going to be able to solve for K. So in place of L, I put what I know about L, and I end up with a minimum of K over 2, and K over 2 has to equal 200. This may seem very strange. Don't overthink it. What's the minimum of K over 2 and K over 2? Well, they're equal to each other, so the minimum is K over 2. So we can rewrite this as K over 2 equals 200. And from there we can solve for K. K has to equal 2 times 200, which is 400. We'll call that equation 3. At this point, we're really almost done. We know that capital is equal to 400. All we need to do is substitute that fact back into 1, the no waste condition, to find the amount of labor we should hire. So labor is going to be equal to 400 divided by 2, which is 200. So notice that this particular cost minimization problem is made extremely simplistic by the structure of their production function. That no waste condition is much easier to work with than your standard tangency condition. So we've done it. We've solved this problem. The cost minimizing input choice is 200 units of labor and 400 units of capital.